We are ready for Class B, and this class will be dedicated to the natural base E, which is also known as Euler's number. Now, E comes about naturally when we do a radioactive decay problem or exponential growth, where you take a derivative of how many particles you have left with respect to time, and that's proportional to how many particles that are there. So in other words, the derivative of n with respect to t is proportional to n. It's like you get the same thing back, and it's the natural base E that does this. And it's one of the 5 most important numbers in mathematics. You can think of the big 5 as 0, 1, pi, I, the square root of -1, and E. And we're going to show you how all of these numbers are related to each other. There's a nice formula which we'll be looking at. And we'll get some insight into what E means using economics and interest rates. And then finally, we'll look at some integral tricks that involve exponentials. And the integral tricks are really cool. It's like magician, theoretical physics, magic, right? To do integrals in a way that is very elegant and cool. So I hope you enjoy this class on the natural base E. Chapter B. What is E? Euler's formula, and integral tricks. And these will use the exponential. So with E. So for B1, what is E? Now, E can be considered as the natural base. Also, it's referred to as Euler's number. You encounter this in physics. For example, in radioactive decay, if you have n particles, and these are decreasing as a function of time as they decay. They're radioactive, but then when they decay, they're no longer radioactive. So these are the radioactive ones. The change with respect to time, they're decreasing, so it's minus some constant, lambda, where the lambda would be positive, proportional to the number. So it's the derivative, gets you the same thing back. And you get the solution, some initial amount, and then e to the minus lambda t. So if t is equal to 0, then you get the initial amount. And then as t goes on, these decrease. And you start out with some n of 0, and then you're going to go, to 0 asymptotically, as time, goes to infinity. This is the n. So if you take the derivative here, you see you would get the same thing back and pull down the minus lambda. So you're familiar with this kind of idea. And if you have a plus, that would be like growth, like bacteria growth, where you're going the other way. There's like an exponential, growth. So the main idea here is to study the function, and the function here, e to the x, dx, and we're going to say, we want to study this word by definition. We're going to start with this assumption. We're going to start here, saying we don't know e to the x in detail yet, but we're going to say that its derivative gives you the same thing back. And we know the answer. Watch this. If you have a power series, and say we don't know this yet, but say if you have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... When you take a derivative, this will go to 0. This will become 1. This will pull the 2 down, cancel the 2, you'll get x. And this one will, the 3 will cancel, and you'll get x squared over 2, or 2 factorial. And if we add one more, x to the 4th over 4 factorial, that would get you, the 4 would cancel, you get x cubed over 3 factorial. But see, this is the same thing as that. There's your 1, there's your x squared over 2 factorial, there's your x cubed over 3 factorial, just shifted over 1. So this is the answer, see, as a power series. Now remember, we did the Pascal triangle, we talked about apples and bananas, and this kind of a definition here. A to the n, b to the 0, picking all apples, there's only one way to do that. And to pick n bananas, so here you have apples minus 1, and then you have b, there's n ways. And I gave you an idea to remember this by this trick. This next one is n over 1 times 2. And that's a to the n minus 2b squared. It's like picking 2 bananas and the rest are apples. 1 banana, the rest are apples, and no bananas and all of them are apples. And then the next one would be n n minus 1 to pick the second, n minus 2 to pick the third, and then since the order doesn't matter, we divide by 1 times 2 times 3. This is n minus 3 and b to 3. So this is an easy way to remember the formula. You have n minus 1, 1 times 2. n minus 1, n minus 2, 1, 2, 3, see, and so on. But now let's look at this case here, where a is 1, and b is x over n. Let's just look at this. Then you have 1 plus x over n to the nth power equals, and now we're going to substitute. Since the a is 1, we would have a 1 here, and b to the 1, 0. b to the 0 is 1, so that's a 1. And then we would have this n over 1, and we would have a, which is 1, so at any power, that's 1. And then we have the b is x over n, so we would have x over n. That's what we would have here. Then the next one would be n minus 1 over 1 times 2, a to any power. Since a is 1, it's going to just be a 1. And this will be x over n squared. And the next one here, just copying down from above, 1 times 2 times 3, would be x over n cubed. And they go on and on and on. But now here's an interesting thing. If you take the limit as n goes to infinity of this thing, look what happens over here. The first term will be 1. The next term, since the n's cancel, you'll just have x. But this next term, you'll have an n squared, and then you'll have an n. But if you're dividing by n squared, the 1 with the n will wind up with a 1 over n. That's going to go away when n goes infinity. So it's the n squared one that we're really interested in. It will cancel the n squared. And that's going to be x squared over 2 factorial. Then if we come over here, we'll have n cubed by these 3. And that's the one we're interested in because that'll cancel this n cubed. And you'll have then x cubed over 3 factorial. And the other terms will have 1 less power of n. See, this here, n cubed is your max power. If you have n squared, if you have n, then when you divide by n cubed, you're going to wind up with at least 1 n in the denominator. So when n goes infinity, you get 0. So this is e to the x. It's another way of writing it. Then that'll bring us to economics to give us more insight as to what's going on. It's kind of neat to use economics here to get insight into mathematical physics. So what we're going to do at this point is we're going to take x to be 1. And if x is equal to 1, then we have a problem that is related to interest. Like say you make 100% on your money. Now no one's going to do that. I mean, that's going to be really crazy. But say if you did, then after 1 year, you would have your money 1. And then you would also have plus the interest. And that would be 1 plus 1. You would have then $2. Start out with $1, you invest it, and in 1 year, like you get 100%, like you get $1 back. So you have your $1 originally, and then plus the $1 interest. So you have $2. But now suppose it's compounded every 6 months. So that means you get, in half a year, you would get half your money. But this is a good deal because this is interest on interest. Watch this. But it's basically a similar idea. Instead of giving you the 100% over the year, we'll give you 50% for 6 months and 50% for the next month. But since you gain a little bit of interest, you're going to get interest on interest. So after 6 months, I have my $1 plus 50 cents. Then when I do the next 6 months, I get this whole thing back again, plus a half of it, because that's the idea, 50% over a 6 month period. So this would be equal to 1 plus the cross term would be a half and a half is a 1, and then 1/2 times 1/2, and you get $2.25. So you get a better deal. Suppose they compound the interest every 4 months, so every a third of a year. So you get a third, and then it'd be 3 times, because we'll do it every 4 months, and after the year you'll have this. So this would be 1 plus 3 times a third plus 3 times a third squared plus a third cubed. You can think of that as your Pascal triangle. You have 1, 3, 3, 1, and then you have here no powers of the second term, and then 1 power of the second term, and then 2 powers and 3 powers. So this would be equal to 1 plus 1 plus, this would be 3 times a 9th is a third, and this is plus 1 over 27. So you put that in the calculator, you get $2.37. Well, now suppose that was every 4 months. This is every 4 months, a third of a year. Suppose you did every 3 months, a fourth of a year, like the 4 seasons. Then you would have this at the end of the year compounded 4 times. And remember, this is 1, 4, 6, 4, 1. So 1 plus 4 times a fourth plus 6 times 1/4 squared plus 4 times 1/4 cubed, and then plus 1/4 to the 4th. See, it's kind of nice to see this review of the other class, the Pascal triangle here, to get the coefficients. And this would be, if you use a calculator, $2.44. So now the question is, suppose you compound it every split second instantaneously. Well, then you'd have 1 plus 1 over n to the nth power, and you would want the limit as n goes to infinity. But now we already know that the limit when n goes to infinity of 1 plus x over n, we already have looked at this equation already, that this equation here is equal to e to the x. See, we already did that earlier. That's the power series, that we did up here. So if we want this limit, we basically want to have the x to be 1. So this is going to be equal to e to the first power, which is going to be equal to e. So in other words, I'm going to know what e is now as a number by this analysis. And that is the money we're going to have if we compound moment by moment. And it comes out to be $2.72, rounded off. If you don't round it off that generously, you would have here 2.71828, and then here, this is in more detail. There's no repeating pattern here, so therefore it's called an irrational number. So an irrational number cannot be written as some ratio. Like if you had a ratio of 5/3, then you'd have a repeating pattern, 1.66666, this kind of thing, going on out. Or if you had 1/3, you'd have 0.33333 going on out. And if you have 0.5, whether you're finished, I mean, you got it. I mean, that's, so you basically have either a 0.5 would be 0.0000 on out. So these are formed by a ratio. This you can't form by a ratio, so therefore it's called irrational. Another example is pi. Pi is an irrational number. You can't take it as a ratio. I remember in grade school, they gave this approximation, and I thought that was cool. 3 1/7, but that's not exactly, that's approximation. So it's not going to be that. It's going to be something else. Now, the number e is also, as well as pi, is also transcendental because you can't get them as solutions to polynomials where you're using your integers. Polynomials would be like 5 cubed plus 2x squared plus 6x, this kind of thing, plus 3, say equal to 0, find what x is. You're not going to get as a solution the transcendental one. But you can get irrational. For example, if you have x squared equals 2, like x squared minus 2 is equal to 0, then x is plus or minus the square root of 2. So see, that would be considered irrational because you can't make a ratio to get square root of 2, but it's not transcendental because it does come out of algebra, equation with a polynomial. And here for the polynomials, you have to use, regular integers. You can't cheat and write down x squared as pi squared. No, it has to be something like here where you have, ax squared plus bx plus c equals 0, where a, b, and c are integers. Okay, so now we move on to B3, which is our joule. the joule. And the joule is Euler's formula. And here, this formula is very, very cool. What it's going to do, it's going to relate for us the big 5 numbers in mathematics: 0, 1, the imaginary number I, pi, and e. But before we do that, let's look at how the secret will work. In other words, we're going to show you with the circle. This is going to be the secret. And the circle is going to get the pi in there. And you already have seen I as a rotation left face in the circle. So the circle is the key to relate I and pi, and also e will get kicked in and be related also. So this is y and this is x, and you can consider the x-axis as the real axis and the y as the imaginary. So like this point up here is plus I, and this one here is minus I. Then that point, well, I mean, technically it's x equals 0, y is equal to I. It's like just totally imaginary. And here, since y is 0, here you could say that's where the x is 1, and here x is minus 1. So in other words, the 1 is this point, I is that point, minus 1 is that point, and minus I is that point. That's your left face multiplied by I, right face multiplied by minus I, about face multiplied by minus 1. So if we look at a general, say, z, some angle theta, then you could write the z as cosine of theta plus I sine of theta. In other words, this one here is the I sine of theta, and this is the cosine of theta. So the cosine of theta is in your real axis line, and then this one is going in the y direction. But now watch this trick. If we multiply by I, we said that's a left face, so won't that be a left face, go 90 degrees, and won't that get you here? Well, let's see. If you take I times z, you'll have I times the cosine of theta, and then minus the sine of theta. Well, if you look at this thing, if this is theta and that's a right angle in there, then this other angle is a complement, complement to theta. So, and since that's a right angle, that means this has to be a theta up in there. And if that's a theta, then this here is going to be sine of theta. And that's going to have a negative sign because it's in the negative direction. And then this height here would be cosine of theta. But since that's along the vertical, that's the I cosine theta. So I cosine theta minus sine theta is indeed that point there. So see, the I helps us relate what's going on here with the rotation. I relates to like pi, because pi is rotation. If you go halfway around about face, you're talking pi, and then all the way around is 2 pi. How do you get e in there? Well, watch this trick. If you take the derivative of z with respect to theta, you then get negative sine of theta, and then you get plus I times the cosine of theta. In other words, you get dz d theta is iz, but wait a minute, we just get the same thing back here with the I and in front of it. In other words, I times, see, this is I times the cosine of theta plus, and then here if I pull that I out, I sine of theta. So what we're saying is that the derivative is I times the same thing. But see, if you take a derivative and get the same thing back, we're talking exponential, like e gets into the game. So here the solution would be for z, and this completes the mystery, how to relate things, the puzzle, I to the theta. Then if you take a derivative, you get the same thing back, which is the z, but you pull down that I. So like the derivative here will be I times z. So then you have this amazing formula. E to the I theta is cosine of theta plus I times the sine of theta. Like, that is wild. And that starts to relate everything together, like all the numbers here that we're looking at. And that's Euler's formula. Feynman has referred to that as our Joule in his famous lecture on physics, one of his lectures on physics delivered at Caltech. In the book, that the Euler formula is the most remarkable formula in mathematics. Feynman was explaining, this is our Joule. So B4, I'm going to say this is our opal. And I'm going to call Euler's identity the opal, another Joule. So here, what you do is you put in pi for theta, e to the I pi. That's going to be cosine of pi, and then plus I times the sine of pi. Now the sine of pi, if you look at here your circle, if you go pi, the sine is 0, just like the sine is 0, 0. So this is 0. And the cosine of pi is equal to -1. Now if we add +1 to both sides of the equation, we get e to the I pi plus 1 equals 0. And that remarkable formula is what I call our opal. It has the big 5, the 0, the 1, pi, I, and e used in the equation once and only once. And that equation, in our gingerbread contest many years ago, who could have the best gingerbread decoration, gingerbread house, the Rhodes Robinson, the Science and Mathematics building won the prize. And they proudly put the equations on the top. The Euler identity, e to the I pi plus 1 equals 0, that's on the roof, and e equals mc squared. Although in the original one they used lowercase c, I think a mathematician actually decorated the cake, our secretary in mathematics, and I went ahead and changed it to capital E, since the physics folks will use capital E for that. And on the rear side of the cake, they had a area of a circle is pi r squared. So these are very important formulas here. We're looking at this one today, the Euler identity, of course, equals mc squared, very important in mathematics. So it's a science building and math building, the Rhodes Robinson complex at UNCA. And you could go here and see more pictures of the cool gingerbread house from different angles and all the nice candy and decorations that were there. Here is the Rhodes Robinson gingerbread house. It was a competition in 2004, which group could make the best house, and the Rhodes Robinson group, the math and the physics folks, sciences, atmospheric sciences, chemistry, the science building basically won the prize. And here we have a very important formula that we're going to be looking at today, and that's e to the I pi plus 1 equals 0 and equals mc squared. And you might enjoy the album here. We're going to open up the album and go visit. Look at this. See, little animals there, and the formula. Nice house. Close up. And it had A is pi r squared on the other side of the roof. So there are the three main formulas that you see on the gingerbread house. There you go. Very nice. There, that's one side with A is pi r squared. And then the other side that has two more formulas. Nice. Here we usually will go with a capital E for the energy for the left-hand side of that equation. A couple of comments here. Let's look at this circle again. And this circle here, we are considering being a unit circle. So when you have the unit circle, let's go ahead at a 45-degree angle here. This is 1. So this is north is I, west, -1, south, -I, and east is 1. Notice that this is square root of 2 and square root of 2 over 2, and this will have an I. So this point here is the square root of 2 over 2 plus the square root of 2 over 2i. Now, the question here is, if I multiply by I rotate 90. So my question is, if I rotate by square root of I, would that be going like 45 degrees? Is that how it works? Because think of this, if I go multiply by -1, I'm here. But if I take a square root of -1, I'm in the middle, like halfway there. See, -1 is rotating over by 180. And then take the square root, I'm here. 90. If I take the square root again, I get 45. Well, this is wild. Let's go ahead and try this. Well, let's go ahead and square. Let's go ahead and square what this point is and see what happens. If we do that, we get then 1, well, we can do a little trick here. We can take this to be the square root of 2 over 2 times 1 plus I. Factor that out, makes it a little simpler. Then if we square this, we get 1/2, and we get 1 plus 2i plus I squared. And this would get you 1 plus 2i minus 1. And then 2i with the 1/2 gets you I. Yeah, it worked. In other words, if we square this, we go up to the I. Isn't that wild? So then you could take the square, you could find the square root of I, or you could find, say, I to the 1/3 power would be to go up just 30 degrees instead of going up 90 degrees. And then you could use this formula with 30 degrees and then like pull it right out. That's amazing mathematics, all right, how that works. And there's a theorem, de Moivre's theorem, that talks about this. In other words, if you take this to the nth power and put an n in there, then you have cosine of n theta plus I sine of n theta. Wild stuff. Now I'd like to show you another derivation of this gem. Let's look at the circle again. Here's a circle. And have I up here. Here you have -1, minus I, and a 1. And suppose we're going to go here where this is an epsilon. In other words, a little epsilon. In other words, we're going to take epsilon to be pi over n, break the trip to go 180, which is pi, break it into n little chunks. All right. So we're going to start with z is 1 plus I epsilon. And if I multiply that by itself, I'm going to then do nudges at that angle. So I can go all the way around and get to my 180. Remember before we did 45 and 45 to get to the 90. And then if we squared that I, we got to the 180. So if we square this, we're going to then nudge around. So when we get to the end, it'll be at -1, and that will be the limit. As n goes to infinity, we break this up. 1 plus epsilon is pi over n. So pi over n. So this is what I want. But we know from our earlier result that when you take the limit as n goes to infinity of 1 plus x over n to the n, that's e to the x. So that means this thing, since the x is going to be I times pi, this is going to be e to the I times pi. And that's going to equal -1. And this is another derivation of the result that we already know. Isn't that neat? It's time for integral tricks. So B5, integral trick 1. And I'm going to call this the real imaginary trick. Suppose you want to integrate from 0 to infinity e to the minus ax cosine kx dx, and we're looking at a is going to be greater than 0, so that this thing doesn't blow out. You know, when you go from 0 to infinity, this will be bounded. And this integral is hard to do. But what we can consider doing an integral that's actually looks like it's more complicated at first, e to the minus ax. We're going to do cosine of kx plus I sine of kx. We're doing 2 integrals instead of the 1. But since the I is there, it'll separate and keep these apart from each other. This is a real part and this is an imaginary part. They won't be able to mix. And since this is e to the I kx via the Euler relation, if that's your theta in there, then this is e to the I theta, as we looked at already, then this integral becomes very easy to do. It's basically doing the integral from 0 to infinity, e to the minus ax plus I kx dx. And that would mean you would have e to the minus ax plus I kx over minus a plus ik from 0 to infinity. Let's just check this. If you take the derivative to go back this way, you would get the same thing back because it's an exponential with the e. And then you would take the chain rule. You would take the derivative of what's up here with respect to x, which is a minus a plus an ik. And that would cancel this, so you would get this. Now when you put in infinity, e to the minus infinity is going to be 0. So you're going to get 0 and then minus. When you put in the 0, you'll have here, this will be e to the 0 over minus a plus ik. And that's going to be real easy. That's going to be 1 over a minus ik, because the minus sign will come in and operate out on that denominator. So here what we do is we can make this denominator real by multiplying top and bottom by a plus ik. And that'll give you a plus ik over a squared plus k squared. Remember, whenever you have like here, a plus b and a minus b, you get a squared minus b squared. So the a squared is here and the b squared is your ik, that whole thing getting squared, which will bring in a minus sign, but cancel that minus sign, you get this. So that means the integral here with the cosine, which is real, has to be the a part, a over a squared plus k squared. And the integral, e to the minus ax times the sine, and we got a bonus, we got another integral here. It'll be the imaginary part, k over a squared plus k squared. Got two integrals done for the price of one. Now we go to B6, which is integral trick 2, and I call this the polar coordinates trick. So say you have an integral I from, say, minus infinity to plus infinity, e to the minus x squared dx. I remember my best friend in Camden, New Jersey, went to Rutgers in Camden, Rutgers South, and freshman math teacher gave this one, which is a little bit unfair since you're not going to be able to do that with, freshman calculus. Didn't really do it, and I remember we had his brother was a physics major, had just gone to grad school as a first year grad school, and he couldn't do it. He mentioned something about a power series, but if you write this as power series, start integrating, you get infinities all over the place. That doesn't seem to make any sense to me. So here, I never knew until I met a guy from Caltech at the University of Maryland who explained the trick to me. And we didn't have paper and pencil at the time. You want to be very careful here and not be operating machinery or doing things when you're trying to do physics in your head or something. So you should sit down on the porch if you don't have paper and be very, very careful. Don't be doing other things. So here's what he did. He says, what we'll do is we'll do I squared. In other words, we'll use the x squared in here, but then we'll do one with the y squared. These are two of the same thing. So, this is I and this is times I, the integral. And then he says, what we'll do is we'll go to polar coordinates. So remember, when you have dx and dy and cover the entire plane, that's an r dr d theta. And here, what we're going to do is a change of variables. So I squared is then, you're going to integrate from r equals 0 to infinity, and then your angle, you swing around 0 to 2 pi, and then you have here e to the minus r squared, and then r dr d theta. So when you take, these two together, you're going to have r squared is x squared plus y squared. So you just have this r squared. But see, this is going to save you. This r is going to save you. That's the secret here. So when you integrate this, you can break this up into two integrals. We can have here the theta going from 0 to 2 pi of d theta. And then r goes from 0 to infinity of r e to the minus r squared dr. So this one here integrates 2 pi, since you'll just get theta, and you'll swing it around from 0 to 2 pi. And then over here, this one here is e to the minus r squared over a minus 2. So if you think about this and go backwards, take the derivative and just check it. So if you take the derivative here, you get the same thing back, but then you'll get a minus 2r. So the minus sign will cancel here, and the 2 will cancel. I'll be left with the r. So like I do get that back when I take the derivative. And so this is going to be equal to 2 pi, and this is going to be minus 1 over 2. And then here, if you put in infinity, you get 0, and then minus, you put in e to 0 is 1. So here, this minus sign will cancel that minus sign, and that 2 will cancel that 2. You'll get pi, and you'll get the square root of pi. That is really a cool result. So from minus infinity to plus infinity, e to the minus x squared dx integrates to the square root of pi. And notice that here, the mystery of how these are related. Here you have the natural base, the Euler number. And here you got pi. You're taking some area under the graph. I mean, if you look at this thing, this is a Gaussian. So this is going to go like up here, and do this and go out like that. So this is e to the minus x squared. So there's your x, and there's your function f of x, which is what this is. And by taking the area under the curve, you get square root of pi. All right, that's how they're related in this profound way. Okay, we go now to B7, integral trick 3, and I'm going to call this the derivative trick. Let's say you want to do this integral from minus infinity to plus infinity, x squared e to the minus x squared dx. Like, what is that, man? The trick is to put in a parameter. In other words, let's consider from minus infinity to plus infinity, e to the minus a x squared dx. Now, if I did this over again, what would happen? All right, let's look at this. If we were to do this with the a in there, there'd be an a there, and there'd be an a in there, and then that a, you would have to put an a here, because when you did the derivative of this, that a would come down again. So you'd have the a, if you had the a in here, you'd have an a there. And if you had the a with that too, you're going to have the square root of pi over a. So that's good for you to look at that carefully. And if you need to write out some of this stuff again, but just put the a there, there's an a there, an a there, an a there, and the a is there. And then here you'd have the a with the 2. So when you took the derivative and the 2ar came down, the a would cancel. So that's actually here given to you as a practice problem to do this. So I encourage you to fill in these steps in more detail. So now what you do is, to get this one, what we're going to do is we're going to take the derivative of minus dda of this integral. So if I take the derivative with respect to a, what I'll do with the minus sign, I'll pull down an x squared. So this will give me, from minus infinity to plus infinity, x squared e to the minus ax squared dx. Now I can let a equal to 1 and go back and get that. So since I don't have a in, I put a in there. I put a because I want to take a derivative with respect to that a to pull down that x squared. So here, d dA pulls down a negative x squared. That negative cancels and I get the x squared. But see, now the trick is just do this thing on the answer for what I is. Because see, this is, you're doing a derivative on the I and you know what the answer is. So minus d dA on this, square root of pi over a. This is the square root of pi. And then we have minus d dA. And we have a to the minus 1/2 power. Just to write that as a power. So then what we do here is the square root of pi, and then that minus sign is still there. With this minus sign is there, but then here, taking derivative, you get minus 1/2 a to the minus 3/2. You know, using the power rule, x to the n is going to get you n x to the n minus 1. Where here the n is negative 1/2, so negative 1/2 minus 1 is negative 3/2. So then you can see that these two signs are going to cancel, and you're going to have here, I'm going to write this out. I'm going to write this out as 1 over a and 1 over the square root of a. So that gets me my 3/2 power in the denominator, and then there'll be a square root of pi. And there'll be a 2 hanging around also. So the answer is, if I want to couple these together, the answer is going to be 1 over 2a square root of pi over a. So all I have to do at the end is let a equal 1, and then I'll have, from minus infinity to plus infinity, e, with the x squared here, e to the minus x squared dx will be equal to 1/2 square root of pi. So it's a square root of pi over 2. So like this is it. We just did a crazy integral here by taking a derivative. And wouldn't you like to take a derivative rather than doing an integral if you had a choice? Of course. And there's a nice little practice problem for you to do here. Look at this. X to the 2n power? What? An infinite number of integrals. By just taking derivatives over and over again, see if you can figure out what this is. We're actually deriving the integral table in the integral book. Okay, and now we go to our last trick, B8, integral trick 4. I'm going to call this one completing the square. I first learned about completing the square and studying conic sections in high school. So the trick is used in different places. Let's look at the integral from minus infinity to plus infinity, e to the minus a x squared plus ikx dx. Later we'll learn, and you may already know, that this is a Fourier transform kind of integration. Note that a has to be greater than 0 here, so that the minus sign ensures that we have bounded situations. The x here, if it's positive, is not really a problem, because here if you have e to the I kx, that's going to get you cosine kx plus I sine kx. And these are bounded. You're not going to go beyond, -1 or +1 for cosines and sines. So there's no infinity is going to show up there. The idea of completing the square is that we do know the integral from -infinity to +infinity, e to the minus, say, a z squared dz. We know this one. This one here is the square root of pi over a. And if we can kind of get this to look like some z squared up there, then we'll have the answer. So I'm going to look at the integral here, a little different one. I'm going to put a plus bx dx. Now, you might worry about this x going to infinity now without the I, but x squared will dominate. X squared is always going to be bigger when you have a big X than an X. And since this has the minus sign in front, this will make sure that you don't have an infinity. Let's look at this exponent. We take the minus a out. You have x squared plus bx over a. Putting the a back in, ax squared, a cancels. For the second term, you get the bx, and you need a minus sign here. It's very easy to miss a minus sign, so let's check that. Minus ax squared, and then the minus gets you a plus, a's cancel, you get bx. Let's focus on this. If this is the cross term, to complete the square, we need the other term, but we can look at that as, say, x squared minus that bx over a. Remember, when you have a cross term, here's a 2. So that means what I have to have here is a b over 2a being squared. Now let's look at this, because see, what we're heading toward is something like this, where if you look at the cross term, it would be x times b over 2a times 2, because you get a 2 in there, and it'd be a minus sign. So the bx over 2a times 2 kills the 2, and then you have the minus sign. So like this is completing the square, but if you add this, you're going to have to subtract it so we don't change things. So we need to put a minus b over 2a squared. So now we have the same thing. So at this point, I'm going to put the minus a back in. And if you do that and then go back to the integral, you have e. You want to put the minus a in there, so minus a x minus b over 2a squared. And here, this will be a minus, so this will be a plus, and put the a back in, b over 2a squared dx. So this part is a constant. So we can write this as minus infinity plus infinity. We can pull this constant out. This is going to be e, and this will be a b squared over 4a squared. 1a will cancel, so that's a b squared over 4a. Say b squared, the 4 is there, a squared, but a over a squared is going to be that, 1 over a. And then this is e to the minus a x minus b over 2a squared dx. And see, this is a z. And a dz equals dx, since that's constants, to shift it. And when z goes from negative infinity to plus infinity, x would go from negative infinity to plus infinity. So we have it. So this integral here is the square root of pi over a, because that part in there is just e to the minus z squared. Here, e to the minus z squared, az squared. And that's the square root of pi over a. So there's the square root of pi over a. So we have the answer. So let's recopy this. Minus infinity to plus infinity, e to the minus ax squared plus bx is the square root of pi over a, and then e to the b squared over 4a. Then if we want to do the original integral, where the b is ik, like this, then when we put in b is ik, the b squared is going to be minus k squared. So here, this will be a minus k squared over 4a. And that's it. Well, we actually have two integrals here. And see, this is a Gaussian. This is a Gaussian here, this part. And if you take this, like the Fourier transform, you get another Gaussian. This is like x here, and this is k. But notice that the a is now 1 over a, so it's an interesting thing where when this one gets wide, this one will get narrow. That's interesting. Okay, that ends the class. I hope you enjoyed it.